Hello and welcome to this Manufacturing Systems Technology module 46. We have been talking about production and withdrawal Kanbans in the previous module, and we also discussed about the way that cyclically you can flow both of them in a manner so that the overlaps of the times between the flow on the right and the flow on the left of the production and withdrawal would actually ensure that you have minimal possible inventory. We also made a statement, a very bold statement last module, where we talked about that the JIT really aims for 1 bin inventory level. Okay, although it is practically not very realistic, but if the approach of this approach, which is actually indicating the lean inventory at every stage, is followed, overall there will be definitely a sizable amount of inventory reduction, which would be able to benefit the system as such. So I was last time referring to the way that we can calculate the active number of Kanbans in a system, so that it can ensure that the system goes trouble free without any breakdowns or without any stoppages. Okay, so we need to sort of evaluate that part today. A quick recap of what would happen. So this is the production side of the Kanban, as had been illustrated earlier. So you can see the production Kanban, take this bin F all the way to the subsequent processing stage. The card is removed and thrown in this container here till and until the full bin becomes empty, and so another empty bin with another card which was actually supposed to be in a full bin. Okay, this is actually a circular card, so this would go as a full bin. So as you can see here from the stacking area, the full container containing a withdrawal Kanban, the circular card right about this particular place, this is a withdrawal Kanban. Goes to the subsequent processing stage SPS 2, and then the moment the full bin goes here, the card is removed from the full bin and kept into this particular rack P2, and another empty bin has the same card put in place actually, and this travels all the way back to the stacking area, as you can see here. The moment this comes again, the circular card actually goes out of here and is able to record on a full bin. The moment the circular card enters a full bin, the rectangular card goes here. The rectangular card is basically the production Kanban, and this initiates the empty bin to go into the previous processing stage or the preceding stage PPS1, from which again a full container can be started by changing the rectangular card to a full bin at the preceding stage from the empty bin which it has received, and subsequently the empty bin can be processed. So there is a flow of the rectangular card, which is the production Kanban, towards the left. So this cycle here which is going on is the production Kanban, and this cycle which is going on here is the withdrawal Kanban, and it's all about the balancing and the overlapping of the various times, which leads to a reduction in the stock area. Some of the rules which are important for these Kanban flow to happen and which has to be followed are the following. Rule 1 is that no Kanban or no withdrawal of the parts can happen from the stocking area without a Kanban going into it. Okay, we now know that a Kanban is a mechanism that controls production on a just-in-time basis, producing necessary parts in the right quantities at right time. So therefore there should not be any overproducing or overflow of materials at every stage, apart from what has already been dictated by the Kanban cards. The subsequent process should come to the the previous stage to withdraw whatever is needed. So it should not overload itself by giving a requirement which it cannot be able to process. So that will do the line balancing disturbance, the disturbance for the balancing of the whole flow. And so muda for all types, that is wastes of all types, would be eliminated in this manner. And if supposing the preceding stage is able to give a defective part, then there has to be a mechanism in place which I will come to later, which is actually known as the emergency Kanban, which will try to initiate the process flow back to normalcy. Okay, but then that would be again recorded somewhere, and based on that the upper management can take a decision about the countermeasures, etc., as to why the defect had come in the process, because of which this emergency Kanban had to be released. Okay, so subsequent process stage comes to withdraw only what is needed, that is rule 2. Rule 3 is do not send the defective parts. By and large, you should be able to give a total quality management at your respective workstation, and you should not be in a situation to produce defective. Plan your systems at the workstation in a manner so that there is 100% fitment of the assembly, or there is 100% deliverability of the work that you have planned for that particular station. The station has to be loaded in that manner so that the guy does not have an overload, or the person does not have an overload, and based on that he produces high quality. Okay. So therefore, do not send the defective parts in any case. Obviously, there is a mechanism in place which would be going through a lot of rigmaroles to actually balance the line again if a defective part is produced. So better not do that. That is the message that is given. Rule 4 is that the preceding process should produce only exact quantity of the parts withdrawn by the subsequent process, which obviously means that without a production Kanban going into the preceding producing process, or production process, it should not get started on its own, and it should not overproduce. So in order to maintain the balance, it should already read the card, the Kanban card, coming from the stacking area, and be able to deliver whatever has been given. So in fact, when we are talking about large automotive assemblies where there are many vendors, the Kanban has to be implemented all the way to the vendor end, where therefore if supposing something is fitting on the line, there should be a real time information of that on the vendor end, so that the stocking area just about gets balanced. It is not that it has a zero stocking area, but the goal of a completely completely foolproof JIT system would be one bin, which is probably not possible. But even if there is a minuscule level of number of bins which are there, the vendor should be balancing that stock area on one side through the production Kanban which is released by the stocking area. The operator on the line who is consuming that should be balancing that stocking area by producing the withdrawal Kanbans from time to time, so that it does not get overstocked. Okay, so this harmony, this process balance has to be maintained. Rule 5 is smoothing of the production. Obviously, the Kanban system cannot operate in a situation when where the production is there is a lot of variation in the overall production requirements which are there. So by and large, the system is more implementable in a situation where the demand is more or less similar, and somehow this is what the customer end of the organization has to ensure, that the demand which comes in has to be planned in a manner so that there is a very good flow within the organization. Obviously, there are many issues in that whole way that this chain is set up from the customer to the manufacturing process, but by and large the smoothing is something that is needed to maintain a inventory less system as Kanban, etc. So if you are in business, if your product is doing well, Kanban can be very well implemented, but if there is a sudden change in the demand pattern or a shock which comes to the system, it may be able to disbalance the system completely, and that is something that you should not aim for when you are talking about Kanban systems or lean manufacturing implementation. So fine tuning of production using Kanban is another big issue which needs to be addressed here. So obviously, at every stage of a production process, be it the assembly stage, or in an automotive for example, be it the paint shop stage or the press shop stage, or be it the weld shop stage, whatever it is, the Kanban has to be very well tuned to each processes, and it should go root back to the the root processes which are typically at the subassembly ends and sometimes even at the vendor end. Okay. So that tuning has to be, the tunability of the Kanban system has to be there as regards all the overall production, and small variations in production requirements can be adjusted sometimes by stopping the process, but still maintaining that Kanban concept. Okay, even if the process is starved at some times, you may create these small variations to see if how quickly the Kanban can arrive for ensuring a smooth flow in the process the moment there is some kind of a stoppage because of some material shortage at some area. Okay, and using overtime and improvements in the processes, if the production requirements increase, you should always ensure that once the Kanban has been fine tuned, it should be maintained at all by all means. Okay, so that's what some preconditions are using the operating Kanbans in the system. Now I am going to sort of go ahead and do some calculations here, where we can estimate what are the minimum number of Kanbans which can play a major role in sort of planning, controlling and reducing the work in progress. Obviously there are two approaches for estimating the Kanban level. One is more on the deterministic side, which talks about the exact numbers of Kanban, and another is on the little bit probabilistic side, where there is a cost minimization which is involved in estimating the probability of having one or the other level of Kanban in the system. So, let us actually talk about first the deterministic model, and in this model typically the number of Kanbans, let us say we call it y at a certain time, let us say y is the number of Kanbans, and let us also say that d is the demand per unit time, and obviously Tw is the waiting time for the Kanban, and Tp is the processing time for the Kanban. You have to now understand the withdrawal and production cycles in terms of these times, because these are some things that you have to make an observation and you have to calculate for a given situation. Okay. Processing time, okay. And A being the container capacity, that means whatever number of parts are coming in one bin or one container. And we also introduce a policy variable here, which is actually the shock absorbent mechanism that you have in place in a Kanban. So, you can always over plan a little bit or lesser depending on what is the regularity of your supply schedules. Okay. So, you basically try to vary this alpha to the minimum possible to have a overstocking situation or even a zero overstock kind of a situation. So, you will have to now study very carefully your process and see what works out for you in terms of alpha. So, therefore, this y can be estimated as greater than or equal to d the demand per unit time times of how much waiting and Kanban processing time is involved times of this 1 plus alpha, which actually overstocks the situation, divided by A. Okay. So, this is actually really the number of containers which are accommodating all the waiting as well as the processing time for a certain demand, and the demand is dictated again by the succeeding process. So, basically this is coming from your station which is prior to you from the customer end. Okay. So, succeeding process. So, that is the demand, and so the demand times of the wait period is really is the number of the demand per unit time times of the waiting time is really the number of items which are going to be there to make a balanced kind of situation as per the requirements, and that divided by A is obviously the number of components per container makes it the number of containers. Alpha is, as I told you, the policy variable which overstocks, because if alpha is mentioned is mostly in percentage. Okay. So, if this alpha is let us say 20% extra, so obviously you are above the demand which causes the balancing by multiplying that with 1.2, okay, meaning thereby that there is a overstock situation, there is a 20% overstock, which actually gives you the determined value of Kanbans, and Kanban is in that case 20% higher because of supply irregularities, etc., which is planned for a certain process. Now, mind you, this is a calculation which goes up to the every single subassembly stage or every stage up to which it can be implemented or up to which it can be doable. Okay. So, obviously the philosophy here is that you have to really take it to a level at a single process level, for example, where there is some kind of an input for in terms of raw material which is coming and some kind of output that the process has. That process can be at the vendor end even, but if Kanban has to be in totality implemented, it has to be at that particular level of breakdown of the the whole structure. Okay. So, at the fundamental most fundamental manufacturing process level. So, going up to that. Okay. So, let us look at a sort of an example problem that we have in question, where we talk about determination of a number of Kanban deterministically, as we have seen before. So, let us consider a production of a certain item manufactured in XYZ company, and its requirements are about 10,000 units per month. And supposing the company has just started implementing the JIT system, and according to the situation, the policy variable now is set at about 40%. So, therefore, about 40% higher stocks are needed at every nook and corner over and above what the JIT system promotes you to have. and the container capacity now is fixed at about 50 items per container, okay, and the production lead time that you have is about 0.50 days. That is what the production lead time. So, you want to determine the number of production Kanbans. Now, he is giving certain other cases. For example, supposing the company has a stable production environment and the policy variable can be fixed at about 0, that means no overstocking situation. So, in that event you can determine how many Kanbans would be needed and what would be the resulting impact in the working process inventory. Obviously, he is talking about other shockers. For example, what happens if the lead time is increased to 1 day because of the labor shortages and failure of the machines, or if supposing it is reduced because of some higher productivity causes and issues up to 0.25 days and because of some process improvements that you had, what would be the number of Kanban in that situation, okay. And there you have to assume obviously a lower value of the policy variable resulting from this process. So, let us actually address these one by one and try to see what we get in. So, we now know that the number of Kanbans are given by this equation y greater than equal to d times of Tw plus Tp by A times of 1 plus alpha. So, obviously, here the daily demand which has been described in the question has been given as about 10,000 units per month. So, if we assume about close to 20 working days in a month, so I can estimate the daily demand as whatever it gets produced in a month divided by the number of days, which is about 500 per day, okay. So, we would estimate this on a per day basis. Obviously, the demand that is available is in per unit days. So, the demand here D what is coming is about 500 units per day as given in the question, and the total amount of production time which is needed, which is actually resulting from both the waiting period and the production period of the Kanban, that is given to be 0.5 or half a day, okay, as illustrated in this question here. So, production lead time. So, then the number of Kanbans that you should have should be actually exactly equal to or even more than the at a operating policy variable alpha of 40%, which is overstocking the situation. The total amount of Kanbans which should be really in place are 500 times of 0.5, which is actually this production lead time, times of the overstocking situation. So, you are planning 40% extra, divided by A is the container capacity. In this particular case, the container capacity has been given to be 50. So, that is how the number of Kanbans result in, and there are exactly about 7 Kanbans, okay, which needs to be in place for a smooth flow of the system. So, that is how you basically operate this Kanban calculation, or deterministically you determine what is the number of Kanban levels. So, I am going to close on now, because in the interest of time the module time is obviously over. The next remaining portion of this particular problem can be addressed in the following modules. Till then, goodbye. Thank you.